inspiration for all types of applications. Engineers are turning to origami for inspiration for all types of applications, from medical devices to space applications and even stopping bullets. But why is it that this ancient art of paper folding is so useful for modern engineering? Origami, literally folding paper, dates back at least 400 years in Japan, but the number of designs was limited.
There were only a handful of patterns, maybe 100, 200 total in Japan. Nowadays, there are tens of thousands that have been documented, and most of that change happened in the 20th century. There were a handful of Japanese origami masters, and by far the most successful of them was a man named Akira Yoshizawa, who created thousands of new designs, wrote many, many books of his works, and his work inspired a worldwide renaissance of origami creativity.
Why is origami this thing that was created for aesthetics mainly? Why is it so useful, I guess, is the question. For like, structural things that were for mechanical engineering or for space applications, like, why does it find itself in so many of these applications? Why is it so useful?
Well, the thing that makes origami useful is it is a way of transforming a flat sheet into some other shape with relatively little processing. This is a folded pattern. It's called a triangulated cylinder. It is bistable, meaning it's stable in two positions. This is one, and then if I give it a twist, this is the other. This really has a bunch of bistable mechanisms in it because you can see how it sort of pops into place. But if you combine the two mechanisms going in different directions, then you get the sort of magical color change effect.
Yeah, that's impressive.
So you look at this and you say, okay, that is a cute paper toy. Is it anything more than that? And the answer is yes.
Does that turn into that?
That turns into that, yep. We're working with a company called Intuitive Surgical that does the Da Vinci surgical robot, where they wanted to be able to insert a flexible catheter with the robot, but the flexible catheters tend to buckle and stuff. So we had developed these origami bellows that if you look down there, there's a hole that no matter how far we move this, that stays the same size on the inside. And what that means is we can put the catheter in there, and as the catheter moves and is getting inserted into the body, it still has supports along the way.
Or for another example, here I have a foldable, bulletproof, collapsible wall. It's based on the Yoshimura crease pattern.
Meaning, if I make this out of a bulletproof material, it can be very compact, be in a police officer's car, and deploy out and be bulletproof.
But would it actually work?
Those in that vial, those are actually bullets that have been stopped by origami.
An intrinsic benefit of origami is that the simple act of folding a material can make it more rigid. I was going to ask you about this.
Yeah.
More origami.
More origami.
Duh!
Yeah.
But I was going to say it's a way of making the can stronger without actually, thinner metal, right?
Yeah.
But for engineering applications, the more common challenge is how to fold thick, rigid materials.
This is polypropylene, okay, very rigid. There's no way that I'm going to be able to fold that into this vertex. So this is an example that shows a couple things. Surrogate folds we can use to replace the creases, and then also that piece of polypropylene folds up, and it also accommodates the thickness in there.
By cutting or scoring materials and adding hinges as necessary, thick, rigid materials can, in effect, be folded. This is useful, for example, in deploying solar panels.
It's a fun pattern called the origami flasher, and you get this kind of interesting flasher motion.
This has been proposed as a design for satellite solar arrays, increasing compactness for launch and reliability in deployment. Functional motions of origami are inspiring new designs for devices, like compliant mechanisms that can complete full 360-degree rotations.
Unlike traditional mechanisms with, bearings or hinges, I can hook on a motor and I can get continuous revolution. I couldn't do that with a compliant mechanism. But it turns out no one bothered to tell the paper folders that, and created a continuously revolving compliant mechanism, which is called a kaleidocycle.
Origami motions are also being used in medical devices.
These would be, the creases in the paper, and we have here now forceps. And so what's nice about this is we could put this at a smaller scale, right, on the medical instrument that go into the body, but then can morph and become the gripper. So it would be very small incision, but then go in and do some more complex tasks inside the body.
A variant of this mini gripper is now being used in robotic surgeries, replacing the previous mechanism and reducing the number of parts by 75%. The origami-inspired device is smaller, but with a wider range of motion. So origami is useful in engineering because it provides a method of taking a flat sheet of material and forming it into virtually any shape by folding. Or if the end product is flat, origami offers a way to reduce its dimensions while still deploying easily. The simple act of folding can increase rigidity. Or origami can take advantage of the flexibility of materials to create specific motions. Perhaps most of all, origami allows engineers to piggyback on the bright ideas people have had over the centuries while experimenting with folding paper. But translating these ideas into practical solutions requires a lot of math, modeling, and experimentation.